Maybe Good afternoon. I was talking to the speaker in the morning, and what I gathered is that there was some repetition. So I hope that because of the repetition, you get to understand some of the things. So you are talking about total factor productivity, panel data, and some also applications of stochastic frontiers. Now, the slides that I have in here, this is related to what we call multiple output or multi-product technology. Now, these slides are somewhat advanced, so what going to be doing is, as before, I'm going to be starting with something simple and then try to get to some of the slides, not all. Okay. So what is the idea of multiple technology? Now remember, I was talking about production processes with only one output. Okay, so we're saying y is a function of some input variables. And I was giving you examples like if you look at farmers, they're producing wheat and they're using land, labor, capital, fertilizer, and things like that. Okay. Now you might just say, well, the farmer is again not only producing like a wheat, but also producing tomatoes, potatoes, and things like that. I mean, in different lots. So the problem is that if you ask the farmer, do you know how much fertilizer you are using for the tomatoes, how much for potatoes, how much for wheat, and how many people are working on each of those things. Usually we don't have the breakdown. So he can tell you that, well, okay, for fertilizer, my total expenditure was like, for example, 5,000 rupees. For labor, it's 10,000 rupees and things like that. So what you have is you have data on the production of various outputs, okay? But so far as the inputs are concerned, you don't have the input allocation for each and every output. So then again, what you can think that you have the input variables, okay, and then output variables, but input variables are not cancel. So the input variables are not specified for each output. So what we'll be doing is to relate it to the production function that I introduced from the beginning. Let's just start with something slightly different, and then again we just um, get to the production function. So instead of one output, since we are going to be talking about multiple output, we start with the technology that we can write mathematically in this form. Okay, let me just get to the back one. So you have f of y, x, okay, and then again if you want, you can put some other variables, but let's say that one, you just close it in here. So what is a vector? Meaning that you have more than one output, and again x is also a vector, meaning that you have more than one input. So what happens if y is a scalar? Then from this production function, you can write simply y is something like this. Okay. Now, but if you have multiple outputs, then you cannot do something like that. So we don't call this a production function. We call this a transformation function. Just a different name. So what this transformation function is doing is you can think in terms of a process in which the inputs are being used in one end and outputs are coming on the other end. So that type of thing. But the difference is that well, you have more than one output. Okay. Uh, okay. So this is kind of the setup. So to start with, I'm not assuming any efficiency. So again, this is a transformation function with more than one output. So again, as I said, what you can think in terms of y is y1. It can be the wheat, and then you have another output y2. It can be tomatoes, or again many other things. But again, two outputs is enough to describe the situation. Okay. So I mean, you can spare, to make some simplification for f. So again, you can think in terms of f of y2, sorry, yx. Okay, so write it out like this, and then f2 is the input function. And if this is the case, it will be clear that if then again you can just write this as y equal to f2x times a or something like that. Okay. Okay, so you can see the relationship going from one output to more than one output. Okay. So now what we need to do is we need to specify some functions. Okay. So we talked about covariance. So you can think in terms of both f1 and f2 are covariance. Okay. So this is just kind of an example. Okay, so if that is the case, we remember the way we write Cobb Douglas. Again, this is just a productive, product of all the inputs and product of all the outputs. So you can just write f1 like this. You can write y1 to the power alpha 1, y2 to the power alpha 2. So this is for f1. And this is x, you can write x1 raised to the power beta 1 and x2 raised to the power beta 2 and so on. And have more than two inputs, right? Okay, so what happens is that if you write it in terms of log, then again it's going to be linear. Okay, so if you take a log, so log of f1 plus log of f2 is equal to log of a. And log of a you can think in terms of being equal to constant plus the term b, that is embedded inside a. Okay, so you can think in terms of writing it out like this. So that means if I write it out fully using this f1 and f2 that I have in there, I can get alpha 1 y1, sorry, log of y1 plus alpha 2 log of y2. And then again, so this is the output function part, and then again like beta 1 log of x1 plus beta 2 log of x2 and so on. And then on the right hand side, you'll be getting beta 0 plus b. Okay. Now, when you write it out, it's clear that again you cannot identify all the parameters. So you need to let me just do it like this. Cannot. And remember when we were talking about single output production function, we were writing y1 on the left hand side and then x's were on the right hand side. So what was the coefficient on y1? There was no coefficient, right? So we were assuming that the coefficient of y1, or you can just say that alpha 1 is equal to 1. Okay, so this is the reason I just said, well, we cannot identify all the parameters. So then again, I said we need to normalize. So in this setup, you need to normalize one coefficient, okay, to be equal to 1 or something of that sort. That means you cannot identify all the parameters. Right? So sort of a normalization is necessary. Okay. So let's just look at this way. So if we normalize alpha 1 to be equal to minus 1, okay, or 1, doesn't matter which way you go. So if you do this, then what is happening is minus log of y1 plus alpha 2 log of y2 plus beta 1 log of x1 plus beta 2 log of x2, and again other is equal to beta 0 plus b. So what you can do is you can take y1 on one side and then the rest of it is on the other side. So if you do that, then you can write log of y1 is equal to, okay, so this looks like a production function, or maybe just write it out like this, alpha 2 log of y2, because I'm taking this guy on the other side, plus beta 1 log of x1 minus plus beta 2 log of x2, and then again I'm bringing this to this side. So minus beta 0 is equal to, not equal to, that's equal to. So I'm taking this on the other side. So this is minus beta 0 or minus b. Okay. So this looks like a production function. Right? The reason I'm just saying that it looks like a production function, you are just saying that, okay, you have one of the y on the left hand side and you use the other y on the right hand side. Now the question is, there is a problem in here. So which y is to be used as the dependent variable? Okay, so if I give you the data and I don't specify which variable is, for example, wheat, which variable is potato, which variable is tomatoes, and then again, I just have a y1, y2, y3 instead of specifying. Then I'm asking you to do the estimation. So the first question would be, which one do you want to put as the dependent variable, like that on the left hand side? So if I give this as an assignment, some people might be using wheat on the left hand side, some might be using potatoes, some might be using tomatoes. So there is no, when I assign it, there is no guarantee who is going to be using which variable on the left hand side. Okay, and because of that, results are going to be all over. Okay, the results are going to be very different than this one group who is going to be using this formulation. They will have one sort of result, and another group who is going to be using log of y2 on the left hand side, they will be getting a different type of result. Right? So although it looks like a production function, this is a problem. And then the other problem is that this is econometric. So this y2 is going to be correlated with the random country. So your estimation that we're talking about, will give you inconsistent estimates. Your estimates won't be unbiased. So this is not a valid procedure. That means even though you can get from here to something that looks like a production function, that idea is problematic. So we always say that, well, if you are dealing with multiple output, you do not do or do not estimate the relationship like this. Okay. So then what we do is you can think in terms of using a different type of normalization. So let's just look at the second type of normalization. So let's just look at this alpha 1 plus alpha 2 is equal to 1. So remember, you have to get rid of one, this is one extra parameter. You have to get rid of that. So 1 is just to use, normalize them to be equal to 1, and this is the second way of doing it. I'm just saying that sum of the alpha is equal to 1. Okay. So if sum of the alpha is equal to 1, you get to estimate only one alpha. The other alpha will be coming from the relationship that alpha 1 plus alpha is equal to 1. Okay. So let's just work it out. If alpha 1 plus alpha 2 is equal to 1, out different. Okay. So let me just go back to this part. Okay. The part I have in there. And let me just get it in here. Okay. Okay, so this was the equation that I started with. Right? And then I'm just saying that, well, I'm going to be using alpha 1 plus alpha 2 is equal to 1 as my normalization. Okay. So then again, you can think in terms of alpha 1 is equal to, this means, again, you can just say alpha 1 is equal to 1 minus alpha 2, or that type of thing. Right? So now again, let's just replace alpha 1 by 1 minus alpha 2. So I can write 1 minus alpha 2 and then log of y1 plus alpha 2 log of y2 plus, I'm not writing all this thing because these are identical. Right? As before, I'm playing with the first one. Okay. Now again, like this means, again, take the bracket out, so get log of y1 minus alpha 2 log of y1 plus alpha 2 log of y2, right? Plus, this is simple math. I'm just going step by step. Okay. So that means log of y1, and then if you look at these two together, you have alpha 2, you have alpha 2. So alpha 2 is common, right? So you can just write plus alpha 2, okay? That something is alpha 1 is equal to 1 minus alpha 2. Uh, okay, this is log of y1. Okay, so you have alpha 2, so I can take alpha 2 common, and then I'm getting it log of y2 minus log of y1. And then the right hand side is exact, I mean, the rest of the term is fine. So now the last line, I have log of y1 plus alpha 2, and then I can write this as log of y2 over y1. Right? So then again, finally, I can write log of y1 and then throw everything on the right hand side. So that means you can do it like this, minus alpha 2. I'm just taking everything to the right hand side, log of y2 over y1, and then the other terms which are going to be equal to beta 1 log of x1 minus beta 2 log of x2, things like that. So what is the difference? This is the final. So what is the difference? The difference is that while in the previous specification, I had log of y1 on the left hand side. And then again, log of y2 was on the right hand side. Okay. So now, if you look at it carefully, you see the right hand side variable in y is in the ratio of 4. Okay. So that is the key. So this is called output distance function. And the reason is that it does not matter which y you put on the left hand side. Instead of y1, if you put y2 on the left hand side, this is going to be y1 over y2. So the right hand side in output has to be expressed in the ratio of 1.
This meeting is being recorded.
Or in short, this is, we call it ODF. Okay. So again, in essence, what is the output distance function? Okay. So output distance function means that you have one output on the left hand side, the other outputs are going to be on the right hand side, written as a ratio of the output quantities. Okay, nothing happens to the inputs. we were talking about, y on the right hand side correlated to the beta, but now it's in the ratio. So both y2 and y1 are going to be related to be exactly the same way. So when you take the ratio, they will cancel. Okay. So you don't have the econometric endogeneity problem. Okay, so this is a popular approach that people use when it comes to estimating, the multiple output relationship. Okay. Okay, so again, as I said, well, if you want to do it with your, and again, this is going to be related to output oriented inefficiency that I'll be talking about in a minute after I finish this. Okay. So again, this is like again, not exactly like a production function. The only difference is that the right hand part of the y variables are to be in the ratio form. And again, if you just evaluate which ratio, well, that depends on what you put on the left hand side. If you put y3 on this side, this is going to be y1 over y3 and then y2 over y3. Right? So all the outputs are going to be expressed in the form of a ratio. Nothing happens to the inputs. Okay. So that's kind of the output distance function. And again, you can do it with or without inefficiency. Right now, I'm talking about a specification without inefficiency. Okay. So now let's just do a different type of normalization. Okay. So we go back to the same function that I was dealing with. Okay. So now I'll be doing this third thing. Okay. So use normalization. Now I'm going to be playing with betas. Right? So think of only two x's, and I'm doing this normalization beta 1 plus beta 2 equal to 1. So remember I told you that there is one extra parameter and you have to get rid of that in some way. So right now I'm just saying that, okay, let's assume some of the betas or some of the input elasticities equal to 1. Okay. We have 2, that's fine. If you have 3, no problem. Any number of x can be there. All you do is like this. Sum of beta j equal to 1 if there are more than 2. Okay. So then again, you do the same manipulation that I was doing. So that if this is the case, you can write beta 1 as equal to 1 minus beta 2. And then again, replace beta 1 in here by 1 minus beta 2. And then again, just go through the lines that I was doing. And if you do that, then you will be getting an expression that will look like this. Log of x1 is equal to, on the right hand side, you will be getting minus beta 2 log of x2 over x1. Okay. And then again, you will have the output quantities, which are outputs are like alpha 1 log of y1 minus alpha 2 log of y2 and things like that. Okay. So what is happening? If you are careful, you will immediately see that, well, what I have done is nothing but switched x with y, right? If you switch x with y, then what I have done and what I got, how I got the output distance function is going to be exactly the same as, again, this is input distance function. That means simply, if you do the math, then you will say that, okay, after doing the first one, you don't need to do the second one. Like if you are taking a test, you might just say that, well, okay, go to the previous derivation and replace x with y, and then again you are done. Okay, so this is called input distance function. Again, this is just a name, and again, this input distance function has similar properties. It doesn't matter which x you put on the left hand side. The only thing is that, well, the right hand side x variable are to be expressed in the ratio form. Okay, and then again, nothing is going to happen to y. Okay, so those parameters are going to be unchanged. We have a minus sign because of the fact that I use normalization beta 1 plus beta 2 equal to 1. If I say beta 1 plus beta 2 equal to minus 1, then you don't have the minus sign. But again, like minus or plus, what I'm talking about is the absolute value of those alpha 1, alpha 2. Now you get beta 2, you are not getting beta 1. How do you get beta 1? Once you get beta 2, you can get beta 1 by looking at this relationship. So you are basically getting all the parameters. Okay. Um, Okay, so the last one is, again, or maybe I should have done it in the third place. So the fourth one is, again, similar to the production function. So let's say our normalized beta 1 is equal to 1. Instead of beta 1 plus beta 2 is equal to 1. Okay, you just use beta 1 equal to 1 as your normalization, and you go back to the function that you see here. Right? So you put beta 1 is equal to 1, and then again, so that means there is no coefficient in front of x1, so then you can write log of x1 equal to, so this is one, and again, throw the other numbers on the right hand side. So you'll be getting, let's just say minus beta 2 log of x2 minus alpha 1 log of y1 minus alpha 2 log of y2 and so on. So this is again sometimes called input requirement function. So this simply says that if x1 is labor, for example, then this tells you that what is the minimum number of people that you need to produce a given level of y1 and y2, and given the quantity of land and labor and land and fertilizer and things like that. So you're picking up one input out, and you just say that well, your focus is to focus is on the labor use, and you just say well, what is the minimum number of labor that I need to use given the quantity of land, fertilizer, and other things to produce a bundle of wheat and corn and that type of thing. Okay, so this is similar to production function. Remember again, if you are observant, you will immediately say that well, 1 and 4 are exactly the same when you replace x with y, because in 1 we had the log of y1 on the right hand side, left hand side. Now I have log of x1 on the left hand side. So if your x and y are flipped, then you're going to be getting exactly this expression. So this is again in a sense mirror image of this production function. Now again in practice, 1 and 4 are not used much because of the fact that you have the same situation. You might motivate in your research that well, my objective is to figure out what is the minimum amount of labor to use. But then other inputs, again your x2, x3 and x2, x3 might be also variable input. You might be thinking in terms of minimizing your cost. Remember when we were talking about cost minimization, we just said that your objective is to use the inputs in a way that your cost is minimized. Okay, so you are not choosing one axis. You are choosing all the inputs in a way so that your cost is minimized. Now here again you are looking at x1 on the left hand side. If I give this project to people in the class, some might be using log of x1 on the left hand side, some other might be using log of x2 on the left hand side. So again, just like the production function that I was talking about, your results are not going to be invariant. Okay, so the question is that who is right? Well, nobody is right. Again, because everybody has problems. Okay, and the problem is again you are just looking at one x, and then this x is going to be correlated with the other term. So you have econometric and quadratic. Okay, so this is again you can think in terms of the ones that I talked about is basically output side and the input side. So the normalization is based on in terms of the inputs or the outputs. Now you might be saying that okay, since I am free to choose any kind of normalization, how about taking one of the alphas and one of the betas and just say that well alpha 1 plus beta 1 is equal to 1. You can do that and you will be getting some expression, but that expression has no meaning or it will be again subject to similar type of problems that we have in 1 and 4. So in the literature, what we use most of the time, again this is kind of the state of the art in the sense that Okay, if you are dealing with multiple outputs, then you have to use either input distance function or output distance function. That means number two or R3. Okay. Now the choice is that, well, what do you want to use? So let's say, well, you are looking at banks. So for banks or any other services, if you go into the hospital produce many different types of outputs. Right? And outputs are the different types of, let's say, the surgeries and other things that they do. So there are many different outputs, and then the question is that those outputs are given. So in that case, your objective is to minimize cost. So you have to serve the patients in a way that your cost is minimized. So in that case, you should be using input distance function. Okay. On the other hand, if your objective is to maximize revenue and your input quantities are given, then you should be using output distance function. So there are some clear cases where to use input distance function or output distance function. But the main point is, again, um, you have to use one of the x's or one of the y on the left hand side, and the variables on the right hand side have to be expressed in the ratio form. Okay. Any question? Okay. So you shall see that, well, this is kind of a very important area of research because we do not deal with, although we spend most of our time in talking about single output, but in practice, most of the production processes are multiple. Now we might just say, well, what would be wrong? Because I started by saying that, okay, you look at the data, and the data says that different types of output that the farmer is producing, okay? Or if you are looking at banks, banks are not producing one output, they are also producing different types of output. Hospitals, there are different types of output. So again, the question is, can you do one at a time? If somebody says that, okay, can I do something like this? I look at wheat, and can I estimate a production function using wheat and all the input quantities? No, that would be wrong because you are looking at wheat, but look at the inputs. The inputs are not specifically used for the production of wheat. The inputs are used for the production of tomatoes and potatoes also, because I don't know the exact amount of these inputs that go to a different type of outputs. If I know, then again, there is no need to do multiple output production function. You can just do a single output production function. Okay. Okay, so that's basically what the tools are when it comes to multiple inputs and multiple outputs. And again, I just did it without inefficiency. So now we can bring inefficiency into the picture, and things would be quite similar. So let's just say, well, we'll bring inefficiency into the picture. I have a lot of stress. So now introduce inefficiency. Now again, the question is, again, what type of inefficiency you want to use? Is it output oriented or input oriented? Okay. So let's just say, well, if you are using output oriented inefficiency, remember that is associated with outputs, right? And input oriented inefficiency is associated with inputs, right? So when you um, transformation function, which I wrote like this, y1, y, and x is equal to a. So now I have to write it like f of y times e to the power u, and then x is equal to a. So this is u is your output oriented inefficiency. So what is happening is your actual output is y, okay, but you are inefficient. So your potential output is y times e to the power u. That means you can produce more than what you are actually producing. Okay. So then again, what you do is, okay, in this case, instead of going through all the algebra, meaning all over again, let me just say that, okay. So this is the case, and again, you use a simplification that is your F1, okay. You just say, well, these are separable. I mean, this is an assumption. If you ever look at the notes that I have in here, I do not assume separability. Okay, but again, that involves again a lot of algebra. But the point is that well, the separability is not a requirement. So if it is separable, then you can just write f1 y and then e to the power u, and then again times f2, and then again this function of x is equal to a, something like this. So your inefficiency part is associated with the output function, and then input function is not related to that because I am using output oriented. Okay, so let me just erase this part because I'm just using output oriented inefficiency. And then again, I'll get to the input oriented part once I finish this. So now going back and just say, well, what is new in here? Your y is replaced by y times e to the power. So y is a vector, but u is a, so e to the power u is a scalar. And this is an assumption. That means you're talking about many different outputs, but there is a efficiency. All the outputs are proportionally produced than what you could produce. Okay. So again, like this is kind of an assumption. So this e to the power u is a scalar, but y is a vector. So you go through the same type of algebra. So if we assume a Douglas functions for both f1 and f2, then again, like I'm not going through all of it. You'll be able to say that log of y1 is equal to, on the right hand side, you will be getting now let's look at this log of y2 over y1. Do you think that there will be, inefficiency is going to be affecting the ratio? If each and every output is reduced by 10%, what will happen to the ratio? Ratio remains the same. So again, although I'm replacing y by y times e to the power u, the ratio is not affected by this. And this one is going to be like this. Because again, I just said, well, all you do is be observant, and then you just see that instead of mechanically doing it all over again, you just say, well, do I want to repeat it? The answer is no. Whenever you see y before, now you replace y by y times e to the power u. Right? Now in here, e to the power u is redundant because again, they will be cancelled, but e to the power u is appearing in here. And then again, you will have minus or plus, whatever I had, I think I had all minus, beta 1, log of x1, minus beta 2, log of x2, and things like that. Okay. And then again, plus or minus b, so let's just put b in there. And again, plus or minus doesn't matter. But again, you want to derive it, be consistent, don't change the sign. Okay. So now again, what you do is, you just say, well, this means log to the right hand side because log is u. So then again, you are getting b minus u. Okay. I want to focus on that part because this is something new, right? And you would like to know whether you need to use a different software or different estimation method. So look, at the right hand side variables, okay, are different now. Before, when I was talking about a production function, I had it only x, right? But in addition to x's, I have the ratio of outputs. Okay. But again, think of this as an additional variable. Okay, so when you run a regression, remember in simple regression, all you do is that while you click on variables that you want to use. You might have 10 variables, sometimes you might have 12 or 15, it doesn't matter. The regression is you just pick the variables that you want to use as independent variables. So the independent variables now are not only the x's, but also the ratio of y's. Now, if there is no y2, so then again, this time will drop and you will be getting back to the standard production function that we have been talking about for some time, right? So now again, when you look at this, again, this error term is the same error term that we started talking about from day one, right? This is a noise and inefficiency. So then again, do you need anything else? That means the scatter code that was used before, right? For half normal or truncated normal, you use the same scatter code, right? Because this is V minus U, right? Okay. So then again, what is happening is that this is the only additional term that you need to use. So this is the only additional term that you have to use. Okay. If it was a single output, you will have simply the excess on the right hand side, and since it is a multiple output, you have to use the ratios of output. If you have three outputs, then you add another term that would be y3 over y1 and on. Okay, and so on. So the number of again outputs does not change anything so far as estimation goes. Okay, and then again, so again, as I said, well, the estimation is not an issue, and the interpretation of inefficiency. What was the interpretation before? We were talking about output shortfall. Again, here you have also output shortfall, but again, that shortfall is not for only one output, but all the outputs. The problem here is that, okay, you have to make the assumption that the shortfall of all the outputs are exactly the same. Okay. I mean, you would like to say that, well, I mean, the model is general enough to allow the possibility of different amount of output shortfall for different outputs. But we have not been able to figure out this different EU for different Y. Okay. Okay, so this is basically again output distance function with inefficiency. So again, I'm just repeating that what stochastic frontier codes that you have seen are the same codes can be used, except for the fact that you need to add these terms. Okay. Now again, okay, if you look at the output distance, input distance function with inefficiency. Now I'm lazy, I'm leaning on this thing, that's why my lines are not straight. Okay. So again, so inefficiency is in the inputs, right? This time. So going back to this, and then if you start with F1 and then Y, and then times F2 times X, but now I have to do something like this. Because your X is the amount of X you are using, but you should be able to use less than that if you are efficient. Right? So now this is again like a input-oriented inefficiency. And on the right-hand side, we have that. Okay. So then again, like you go through the same lines of algebra, and then you will be saying that, okay, log of x1, okay, on the right-hand side, you'll be having beta 2 or minus beta 2 log of x2 over x1. Now we just change this to this. Because x's are replaced by x times e to the power minus eta. What will happen to the ratio? If all the x's are changed proportionally, then the ratio is not affected by eta. So there is no eta in there, but there is going to be eta in this side. Okay, and then again minus alpha 1 log of y1 minus alpha 2 log of y2 and so on. Okay, so let me just put plus b in here, and then when you remove this eta from this side, so log of x1 and then minus eta, right? I'm taking it to the other side, so that is going to be again everything else in here, and then again b plus eta. Right? So this is again they change the sign from v minus u to v plus u, that type of thing. Right? So this is again a cost function formulation. So going back to what this data code was saying, that okay, you need to say that what is the orientation? Is it output orientation or input orientation? Now you need to tell SCADA or whatever software you are using, because that will dictate the computer to use the appropriate method. If you say the orientation is output, then it's going to be v minus u. If you say that orientation is input, then it would be using v plus u. Okay. Now here again we are changing notation. Instead of u, we are saying eta. But mathematically, what is happening is plus or minus, right? Plus when you are using a cost function or input distance function, minus when you are using a production function or output distance function. Okay. So again, you don't need to know anything new. So no new uh, estimation technique is needed. Or no new okay. So you see that while knowing how to run SFA can give you a lot of things. I mean, it's not that you have to learn something new for every model that you are using. Now, I'm not sure whether you were here in the, I mean, in the morning session. Again, when he was talking about that, he also introduced stochastic frontier, and he was not talking about production function as such, but when I was talking to him, he said about he mentioned some other potential applications, and I'll be also talking about this non-standard application sometimes tomorrow. I mean, one of the sessions. Okay. That means you don't have to always think that, well, okay, all I did in the whole in a period is talking about production function, and you might be saying that, well, that's not what I want to do. I want to do something else. Okay, so I'll be giving you some examples, and then again, I will be saying that, okay, what you want to know in order to use this tool. What type of situation you have to encounter to use this particular tool. Okay. So again, this is we're talking about input and output distance function. What do you want to do? Okay. So then again, this is all done. Now let me talk about translog production function because you are or I've been talking about this Cobb Douglas. So again, the Cobb Douglas. What is a Cobb Douglas? Cobb Douglas, I told you that this is log linear. So if I have f of x and I just say what this is Cobb Douglas, what it means is that what you can write it as a linear function in log Cobb Douglas, then you can write log of y is equal to the function, a function, right? So this is going to be beta plus sum of